All right, so this is our final project for Quantum Fundamentals. It's presented by Olivia, myself, and Trevor. All right, so our chosen prompt was to examine a system consisting of two or more spin one-half particles, focusing on either quantum entanglement or magnetic moments of particles. So the plan or roadmap, I guess, for our presentation, first the math of spin one half. And I know we went over this in class, but I don't think it'll hurt anything to have people caught up to speed and to make sure that no one's lost. And then number two, we have discussing quantum entanglement and kind of discussing the concepts around it and how it works, and then also discussing any limitations on that quantum entanglement. And then I'm going to hand it over to Olivia. She's going to talk about an example of quantum entanglement and the magnetic moment of particles. Lastly, Trevor's going to take over and he's going to go in depth about how multiple particles work with spin one half, and so we can see the differences between one particle of spin one half and multiple particles of spin one half. All right, so first the review. We know that eigenvalues are measurable results, so either plus h bar over 2 or minus h bar over 2. And we can also get those from our spin operators below. Now the probabilities. The probabilities are the norm squared, or in other words, itself multiplied by its complex conjugate. And now keep in mind, if you don't have a complex component, it's just the coefficients squared. In the example below, I use 1 over root 2 multiplied by plus ket plus minus ket. Of course, we get a 50-50 because of the 1 over root 2. And of course, it doesn't have a complex component for this example. Lastly, the Hamiltonian. We know from class that the Hamiltonian has a component of the magnetic moment and the magnetic field that the particle is subject to. And keep in mind that this Hamiltonian, this equation for it, is for one particle. We'll see Trevor's slides where it's detailed how the Hamiltonian looks with multiple particles in spin one half. So now we're going to move on to quantum entanglement. And what are the consequences for sharing two particles? Well, we know that if you have two particles measuring the same direction and they're entangled, if you take the measurement of, let's say, particle 1 and you measure in the same direction, you now know the spin measurement for particle 2. And that's an important piece. Now, keep in mind, though, if you do measure particle 1 and you measure a different direction for particle 2, you're going to be getting a different chance for that, for having opposite spins. So you might be saying, okay, if we know that the spin of particle 1 affects the spin of particle 2, is that still random? Well, in a sense, yes. It still is random for particle 1. It still rolls the dice for 50-50 every single time you measure it. Particle 2, on the other hand, it's still technically 50-50 for this case, but it still relies on particle 1. And also keep in mind that these particles that we're talking about don't have an intrinsic spin, or don't have an intrinsic real property, right? They're not spin up before we measure it, or they're not spin down before we measure it. They just they have that measurement when we measure it at that moment. And also keep in mind that when we do measure particles, the photons that hit our eyes so we can see also affect those because they're just so small. So now that we covered the basics, how that kind of works, we'll talk about the limiting factors of entanglement, right? We know that, particles depend on one another, right? Especially their spins. So is there any distance that it, maxes out at or just stops working? And the answer is no, surprisingly. There's no distance really that stops quantum entanglement from applying, right? You can be light years or even just a few feet away from each other, and you end up with quantum entanglement still working. But there is a specific way to break quantum entanglement of two particles, or multiple, and that is to force those particles to be in a certain state, right? There's an important distinction between measuring particles and forcing them, right? Measuring is not forcing, it's simply observing. And when you force a particle, let's say in an experiment, you break that quantum entanglement, and now those rules that we previously talked about no longer apply. And of course, we talked about distance. So you might ask, okay, does this break any laws, especially the speed of light? And the answer is, again, no, it doesn't break anything. And the reason for that is because we're not transferring any information, right? There's no radio waves going from particle 1 to particle 2 to tell it what to do. There's no information being transferred, so we aren't breaking any rules here. So now I'm going to pass it over to Olivia so she can cover more about quantum entanglement.
Okie dokie. So I am going to start talking about an example of quantum entanglement today. And our first bullet point says, to study entanglement, scientists generally use a crystal called barium borate. This type of crystal, specifically barium borate, allows for scientists to generate two entangled particles from just one. Before particles of crystals are measured, they will be in a state of superposition. As we know from class, in this state of superposition is that each particle will be both spin up and spin down at the same time. The direction of spin is then measured for each particle. For this specific example, it is important to note that entangled particles are sent off in different locations as well, which will also be touched on kind of at the end of these few bullet points. And when the direction of the spin is measured for each of these particles that are at two different positions in space, there's a peculiar correlation found. And that is, when measuring the direction of spin of one particle, then repeating the measurement for the other distant entangled partner, we notice a specific correlation. This correlation is that depending on the setup of the experiment, if one of the particles is spin up, then the other is spin down. Like I said earlier, depending on the setup of the experiment, the spin may also be both up and down as well. And then I just tried to visualize this in a way that makes sense from what we did in class. So thinking back to the arm exercises we've been doing throughout the term, if we think about the arm exercises we did in class, they were focused on a singular particle, just typically one spin 1/2 particle. But the prompt in this case is asking to talk about two particles. So to better visualize quantum entanglement, you can think of two students in different locations throughout Lake Winnegar, spinning their arms at the same rate or angular velocity, so that when you spin your arm and the other student is spinning their arm, their arms will end up at the same position at the same time, just in different points of space. That makes sense. Although it seems strange that two subatomic particles, even if they're separated by like billions of light years of space, they are linked together. Like that's why in the example relating to the arm exercise, I said just think of two different students in different parts of Winnegar doing the same thing at the same angular velocity. Those are our particles that are linked together. So if something happens to one particle, or in our situation, a student, it will also change what happens to the other student that it is partnered with across space. So if my arm starts to spin faster, like there's a change in this, my arm starts to spin faster, my partnered particle or student across Winnegar is also going to be experiencing the same change. And then here is just a picture of barium borate. And then this is just kind of a cool Jimmy Neutron-esque visual representation of two linked particles. So now I'm going to touch on the basics of magnetic moment, which should be a review for most of the people here. But what is magnetic moment? Well, magnetic moment, also known as the magnetic dipole moment, is something that can be defined as the maximum torque experienced by a particle when placed in an external magnetic field. We also know that the magnetic moment is in fact a vector. So how is magnetic moment created? Well, the magnetic moment is a vector that is typically aligned and parallel to magnetic field lines and is created by spin angular momentum and the motion of electric charge. Breaking it down even further, what is spin angular momentum? Spin angular momentum is based on an object's internal motion and is represented by our favorites h/2 pi, which we see a lot throughout our calculations this term. The second component, what is motion of electric charge? It is a key concept to magnetic moment and understanding magnetism. And this motion is what helps a particle produce a magnetic field. Now I'm gonna hand it on over to Trevor.
All right, continuing on with what Liv was talking about. Hi, my name is Trevor, and I'm going to be talking about spin-spin interaction, mostly talking about magnetic moment, which is what Liv was just talking about in the last slide. So with any system consisting of more than one spin hat particle, you can see the Hamiltonian that Zach was speaking on is equal to 2a over h bar squared times the dot product of the angular momentums of the both particles. With more than two particles, it would just be multiple dot products. The example I was looking at was the angular momentum of a proton and an electron, because both of those are spin half particles and also have a magnetic moment that's intrinsic to the particle. This is due to the fact, so the angular momentum here, like Hamiltonian being dependent on the angular momentum, is due to the magnetic moment that interacts with the magnetic field resulting from the magnetic moment of another particle. It actually, I guess more specifically, the spin of one particle is interacting with the magnetic field resulting from the magnetic moment of the other particle, and vice versa. So each particle has a two-dimensional state, which we learned in class. And so that means that a two-particle state specifically would have 4 dimensions. And you can pick a pure basis if you like. So plus C, plus C, plus C, minus C, minus C, plus C, and minus C, minus C. And so those are the 4 dimensions that we're looking at when it comes to a two-particle system. So with this basis, we have the fact that the plus C and minus C are both spin 1. And then in the other two basis states, since we have the ability to add spin, right? So the spin of both, the spin of the total system is equal to the spin of each particle added together. So depending on the phase between them, the plus C, minus C, and minus C plus C states can either have a total spin of 0 or 1. So in a spin 1 state, through the Stirner-Gerlach experiment, we can see that there's a 50% chance that both particles will be either spin up or spin down when we're looking along the x-axis. And then in the spin zero state, there's a 50% chance of either one being spin up or spin down. But then that means there's always a 100% chance that the spin of both particles will be opposite to each other, creating a spin zero state. And these are our sources that we used. And that's all. That's our presentation. Thank you.